All right. So for today's video, I'm going to be going over normal standard distribution. And this is really just analysis of probabilities using a z-score. So let's go ahead and look at what a z-score is. So a z-score is a standardized score that analyzes data in terms of relative standing to the mean of that data set as well as its standard deviation. So the z-score is a measure of position in the data set, describes a specific it compares a data point relative to the mean and the deviation of the data set. So to review that, we're going to look at the formula. So the formula for Z is you take a data point and find the distance it is away from the mean, and then you divide that by standard deviation. So this is going to give you a Z-score for this particular data point, and it's going to tell you where it stands relative to the mean and standard deviation. So for example, I have Z equals 1.67. This means that whatever value I'm looking at the data set, it has a Z-score of 1.67, which is 1.67 standard deviations above the mean. And if I had a Z-score of -4, that means I have 4 standard deviations below the mean. That's where that number stands in the relativity of that data set. A Z-score does have some type of threshold. So a z-score, normally, my threshold is 2. So you want your data to fall within 2 standard deviations from the mean, and that's where it's supposed to be. If the data falls more than 2 standard deviations away from the mean, or less than -2 deviations, or 2 deviations below the mean, then that tells you that that specific data point is either significantly high or significantly low. And so it's that difference, it occurs between the mean and standard deviation with that data point. So now looking at standard normal distribution, there's 3 properties of standard normal distribution that we must look at. Number 1, the data must have a bell-shaped curve. Okay, my mean has to be 0, and it has to be the highest and centered peak of the data set, and my standard deviations are 1. So this gives me that understanding of what is it that I'm looking in terms of mean and standard deviation. So I'm going to also explain density curves, because this right here is a density curve. This area all under this curve is an accumulation of probabilities. So a density curve, I'm going to explain it using the property of rolling a die. So if I roll a die, throw it out, I have 6 possibilities. I can roll a 1, a 2, a 3, a 4, a 5, or a 6. And these are all independent events, which means that they all have the same probability of occurring. So each of these have the same probability. There's a total of 6 sides, and landing a specific value is 1 out of 6, which converts into 16.67%. So looking at that, I still have here now a density curve, which is literally this uniform probability across the way. But I can use this density curve in the area under it to measure or to predict specific events in occurrence. So, like for example, what's the probability of me rolling at least a 3? That means I can roll a 3, a 4, a 5, or a 6. Notice that's the addition rule from prior chapters. But it really is, like, here's the probability of a 3, here's a probability of a 4, here's a probability of a 5, here's a probability of a 6. And if I look at this area here, which is 4 by 0.167, that's going to give me the probability that I have here. So let's see, 0.167 times 4 gives me a 66.8%. So this probability is 66.8%. Or if you notice here, I shaded 66.8% of this entire curve. Okay. Okay. Let's look at now understanding probabilities using z-scores. So again, if I'm going to be using a z-score, my data must be normally distributed under those 3 conditions. And again, here is my density curve. It has a center of 0, and then my standard deviations are measured in 1 unit, okay? Area under the curve will always sum up to 1, okay? So in analyzing probabilities, we will need to use the Triola tables. These are the tables that are found in the back of the stats book, and you'll be able to understand those probabilities. So what these Triola tables are is it lists all the possible z values that are here, and it'll indicate a left-ended analysis of what that probability is. So it's just like in the previous example I showed accumulated probability. That's what these Triola tables are. So I'm going to start with an example. Find the probability that z is less than 1.27. So here's my z curve. I'm looking at 1.27. 1.27 falls between 1 and 2, closer to 1. And it's saying less than, which means I'm only focusing at this left-ended part here. That's what I'm focusing on. So if I go to my Triola table, I'm going to look at 1.2. So there's going to be rows that say 1.1, 1.2. So I'm going to look at 1.2. And then there's columns that go 0.0, 0.0, 0.01, 0.02, all the way to 0.09. I'm going to go 1.2 here and then to the 0.07 here, because that's what this number gets. So this 1.2 is the first thing I look at on my rows, and then I look at the column of 0.07, and that's going to give me the value that I need. So the probability of achieving a z-score that's less than 1.27, the table gives me a 0.8980. So then this means that the probability that a z-score is less than 1.27 is 89.80%. Notice that this means that this table of values here is shaded at around 90% of it, right? Okay, now let's look at this other one. What's the probability that my z-score is greater than? So now it's asking for this part here. Remember that the entire area under this curve is 1. I already know what this area is here, and I need to know what this is. If this entire thing is 1, and I know what this is, I can just find that difference to then derive this little area to the right. So that's exactly what this formula is saying. It's literally the complement of this. To get the probability of z being greater than 1.27, all I have to do is take 1 minus the probability of being less than 1.27. That's going to give 0.1020, which means that's 10.20%. So this area here is 10% of that. So remember, it's a complement. These are right here. So notice 1 is the entire curve. Subtracting the left-ended analysis is going to give me the right-ended analysis. So moving into the types of analysis for z-score analysis. Again, left-ended, and this is the one the book used. The tables that give you the calculations are left-ended. To use right-sided analysis, we have to use that complement of the left-sided. So again, to find the probability of z being greater than a, that means 1 minus the probability of z being less than a. And it's exactly what we just looked at right now. Okay. Now let's looking at the in-between one. The in-between one, remember the book gives me left-ended analysis. So in order to get an in-between analysis, I look at the left-ended analysis of the furthest, and then I subtract the left-ended analysis of the most left z value. So here, you must also notice that A is greater than B. So B will always be, A is less than B. B will always be greater than A. So notice B is greater than A, so it's the one with the most to the furthest right. And then A is the one that's closest to the left. That's the one that has less density there. Okay? So this is the formula. To find an in-between value, I look at the left-ended analysis of the largest z-score subtracted by the left-ended analysis of the smaller z-score. Okay, so let's look at a probability now. An example, what is the probability of achieving a z-score that is less than, again, very important, 2.07. So the best thing we can do here is draw, identify the z-value, shade based on the requirements, and then verify, find the value on the t-table, and then write the sentence. So here I am. Here's my z-curve. Again, zeros in the center, going by 1 units to the right, 1 units to the left, right? And it says 2.07. So 2.07 is right here, relatively close to 2. Less than means I'm looking for this accumulated probability. So again, I'm going to look at the book, and that's going to give me 0.9808. So the probability of achieving a z-score that is less than z equals 2.07 is 98.08%. And your shading in your picture should be able to justify this percentage. Am I shading about 98% of my curve? Okay. How about a z-score find the probability of achieving a z-score that is greater than. So now I'm looking for greater. These are context clues that are going to show you exactly how you're going to shade. Z is negative 1.52. Again, draw my little z curve, identify the z value. Negative 1.52 is over here between negative 1 and 2, closer to negative 2. And I'm going to shade to the right because it's asking for the probability of it being greater. So again, because it's greater, it's a right-handed analysis, which means I must take 1 minus the left-handed analysis of that z value. And that's going to give me 1 minus 0.0643. You find this value here on the book, on the table. So that's going to give me 0.9357. So the probability of achieving a z-score that is greater than negative 1.52 is 93.57%. Again, check with your drawing. Am I shading a majority of my things, since 93.57 is a majority? Now, what happens if I want to do an in-between of these two z-scores? You recognize that this is A and this is B, since negative 1.52 is less than 2.07. Okay, so again, to find this in between, I take the left-handed probability of the larger z-value subtracted by the left-handed probability of the smaller value. So taking these two values, I get 0.9165. Draw it out as well. So remember, here's my drawing. And the probability of reaching a z-score that is between negative 1.52 and 2.07 is 91.67%. Okay. So now what happens if I ask you, what's the z-score that gives me a left-handed probability of 87.49%? So now we look backwards. Here we would have to look at the table, find the probability first, then derive the z-value. So here, I don't know what the z-score is. Notice there's an unknown, but I do know what the probability is. And then I go into the table and I find it, and it gives me 1.15. So now I proceed to drawing it out. So I recognize that this value here is going to be 1.15. Okay. And it's 87.49. So again, make sure that the picture validates your answer. So the z-score that renders a left-handed probability of 87.49% is z equals 1.15. Okay? Hope you enjoyed this one, and stay safe, everybody.